Hey, in this video, we are going to discuss the scaling and reflections of a graph of a function. This is sort of like transformations that could be performed on a graph. It's a kind of generalizations to the two operations we have discussed in the previous video. In the previous video, the operation we was discussing is shifting the graph horizontally along the x-axis or shifting the graph vertically along the y-axis. In these two operations or transformation, the graph is sort of like translated. Right? The translations of the graph horizontally or vertically does not change the shape of the graph. It only shifts the graph as a whole either to the left, right, or up, down. In this topic, we are going to talk about the different types of transformation, which is not translation. So here we are going to talk about how to, say, compress the graph horizontally, vertically. You can also compress or stretch the graph vertically. In these operations, the shape of the graph in general will become different after you compress or you stretch the graph either horizontally or vertically. There's one more types of operation that will be discussed in this video is what we call reflection. You can reflect the graph of a function on the x-axis or on the y-axis. So you have to understand in this case what you meant by compressing and stretching of the graph horizontally and graphically, and how to obtain the expression for the function after this operation. So to begin with, let us look at an example of what you meant by vertically stretching and compressing a graph by a factor of 3. So there are two things that we need to be understood. The first thing is the reproductions of the stretching and compressing effects by reproducing the shape of the graph after the stretching or compressing. So when you compress or you stretch a graph, you have to specify what is the factor to compress or to stretch. And the factor of stretching and compressing has to be a number which is equals or larger than 1. If the compressing or stretching factor is equal to 1, that amounts to no stretching or compressing. So we have to perform the compression either vertically or horizontally. The compression or stretching of a graph horizontally or vertically will result in two totally different looking shape of the function. So let us do it one by one. Let us take an example of compressing and stretching a function of y equals to square root of x. Now what you mean by saying compress a function by a factor of, say, 3? So the correct way to understand that statement is by looking at the shape of the function geometrically. So let me try to reproduce this idea on a whiteboard. Okay, so let's just look at an example of y equals to square root of x, which is what is represented by the figure 1.57. So I'm waiting for the whiteboard to display itself. The line is a bit slow here. Okay, so say we have a square root function, and the square root function looks like this. It is defined only on the positive values of the real number, and this is y equals to square root of x. So when you compress a function by a factor of 3, for example, here we write the compression factor to be 3. So what you mean by compressing a factor? Let me write down. Compressing the graph, compress graph by a factor of k equals to 3 vertically. The statements that is written down here amounts to saying that for every single value of x, you just simply choose any values of x on the graph. So here x is fixed. So this is the corresponding values of y on the curve of square root of x, where x is fixed. When you compress the function by a factor of 3, what you meant is that you take the values of y at this point and you compress it by a factor of 3, meaning you would translate it to another point which has a value which is 1/3 the original value. So if you compare this value and this value, the ratio would be a factor of 1/3. Okay, so every single point on the curve of y equals x squared at the fixed values of x here, you would bring this point to a number which is smaller by a factor of 3. So probably if you bring it down by a factor of 3, then this point will be more or less landing on 1/3 of the height. So for every single value of the point here, you bring down this point to 1/3 of it. This point you bring it down to 1/3. This point you bring it down to say 1/3. So after you have done that, then you would be able to obtain a set of points which is obtained from the original point by mapping the values of y on this point to a number which is lower by a factor of 3. So you draw this curve which is derived from the original curve by compressing the factor of 3. Then this is a new function. The function y1 here, if you compare the values to the original values of y, say you compare these values of y1 to these values of y at the common values of x. So no matter what values of x, as long as you compare the values of y to y1, the ratio of it at the fixed values of x is equals to k equals to 3. So in that sense, we say you have compressed the function of y equals to square root of x by a factor of 3. So y1 would be the resultant curve obtained by compressing the original function by a factor of 3. Be reminded that the factor of compression must be an integer equals or larger than 1. So based on this mathematical expression that relates the values of the original function to the compressed function, which is always equals to 3. No, I think that is something which is not quite true. So I'm sorry. This is not 1 equals to 3. The ratio of y1 to y is always 1 to 3. So that should be equal to 1 over k instead of k. Okay, so that is a mistake that I have to correct. So the ratio of the values of y1 to the original values of y is always equals to 1/3 because y1 is smaller by y by a factor of 3. So that is the mathematical relationship that relates the values of the y and y1 on the same values of x. So that is the mathematical relationship that allows us to then obtain the relationship between the compressed function along the vertical directions to the original function, which is y over k. So that is to say, if you take an original function y and you replace all the values of y by k, then this operation will result in a new function y2, where y2 is just the original values of y replaced by y over k, and you write this as y over k. So here the compressed functions is just 3 for our case. So if you set this to be 3, then you carry out this operation. The compressed function y1 then has the formula of square root of 3 divided square root of x divided by 3. So let us try to demonstrate these situations using Mathematica. So I'm going to show you the Mathematica functions. Here, let me define, say, y, which is a function of x equals to, say, square root of x, right? So I'm going to plot this function for y of x, where x is, say, going from 0 to 1. So this is the function of square root of x. So let me plot the legend to show the legends. So if I have a function of y1, which I have shown to be equals to y of x divided by a factor of compression 3. Here I define the values of k to be 3. Okay, just to make the k to equals to the example I just mentioned. So I expect that when I plot the function of y1, y1 should be below the original function of y by a factor of 3. So I'm going to plot y and y1 together on the same plot, and you can see that indeed y1 is lying below the function of y, and if you take any single values of the point on the curve y and y1, the ratio is always 1/3. Now, for example, if I say y1 evaluated at, say, x equals to, say, 0.5, right? So I take this ratio to ratio of y1 at 0.5 and y at 0.5. When I press the button, this is amount to, say, I am taking the values of y1 at this point here, and then the values of y at this point. So I don't really know what these two values is, but the ratio of these two should be equals to 1/3. Right? So that is expected. So that's how you reproduce or reconstruct an compressed function, a vertically compressed function based on a given function. Here the given function is y, which is square root of x. You compress it by a factor of 3, then the compressed function always lies closer to the x-axis than the original function from the x-axis. So that is how you make compression, vertical compression. You can also make an stretching, like a vertical stretch. You stretch the original function by, say, a factor of 3. When you stretch the function by a factor of 3, that is amount to saying this. Okay, let me try to reproduce the argument again. So you have a function of y equals to x, square root of x. So when you stretch it vertically for a factor of 3, so 3 stretch vertically by a factor of k, where k is the number, integer number larger than 1. What you actually mean is that for any values of x lying on the y-axis, say you have some arbitrary values of x, then this is a values of y on the original factor. When you stretch it by a factor of 3, what you mean is that every values of y on the curve is to be stretched by a factor of 3. So this is a 1 factor. Well, maybe I should redraw this just to rescale my graph, okay, or else it will be too large. Say this is the original function. Okay, so when I stretch it by a factor of 3, then this point will become 1 time, 2 times. So it will be somewhere here. This point will stretch to the factor, to the values of here. So where this is 3 times higher than this. Not only this point will be stretched by a factor of 3, this point, for example, will also be stretched by a factor of 3 up to here. But this is the 0 point. So when you stretch it by a factor of 3, this point will not change its value. Right? So if you do this every single point on the y equals to square root of x curve, then the new curve that you obtain would be like this. Right? So if you take any particular vertical line at the fixed values of x, the values of y on the original curve at x and the values of y2 at the same point, where this is the curve of y, well, maybe I call it y3 instead of y2, okay? So the values of y3 at this point is the point here. So if you stretch this by a factor of 3 to y3, then the ratio of this would then be equals to 1 over 3. So this is a relationship for the stretching of a function vertically. So to summarize, if you have the original function y of x, to stretch it vertically by a factor of k is amount to say that for every values of y, you replace it by a factor of k times y. So after this operation, the function of y will be projected into another function called y3, where y3 is obtained from y2 by replacing is obtaining from y by replacing y with ky. So that would then become k times y. So here the k is just the factor of stretch, and here you have an x. So this function of k times square root of x amounts to a stretch function, a vertically stretched function of the function of square root of x. So you compare this to y2, right? y2 is original function divided by a factor of k. y3 is the function multiplied by k. So this is the formula for the compressed function, vertically compressed function. This is a formula to describe a curve which is stretched vertically along the vertical directions. So here, let me try to reproduce the function of y, the function of y3. Here is a function of y2, which I'll define as square root of x times divided by k. y3 is the square root of x multiplied with k. As explained in the previous slides, this y3 is an stretch function, and this would be an compressed function. This would be a vertically compressed function. This will be a vertically stretched function. So let's see if this is indeed the case. So I'm now displaying y2, y3, and y at the same plot. Okay, so here you can see this is original function y2. This is an function which is obtained from the original function by compressing it by a factor of 3. So this is y2 and compressed function from the original function. y3 is a horizontally stretched function, that is, for every values of y, it is stretched to 3 times larger. Therefore, y3 is 3 times larger than y, whereas y2 is 3 times smaller than the function of y. So that finally conclude that indeed to compress the function, you just divide the function y by a factor of k horizontally, vertically. In order to stretch a function's vertically, you just multiply the original function by the stretch factor of k.